So I will be speaking about how you can use solid-state NMR to look at battery materials and intermetallic phases. And for this, you need, as you will also see later, ultra-wideline concepts. So how to broadband excitate, to perform broadband excitation, and so on. So if you think about an NMR pulse, what you need is, of course, you need to know how it's created. This is what the NMR console does, of course. But you can also think in terms of what is the optimal shape of a pulse. We normally think in terms of a square pulse. That's one option. I'll also show this a bit later. You can also think about other possibilities. And for instance, what is the optimal power distribution? How do you get this? How do you obtain broadband excitation without using too much power? And how can you reduce power reflection? Of course, if you have an oscilloscope, you can just connect this to your spectrometer, and you can actually watch the pulses on such a thing here. So on the spectrometer, the pulses are generated using a waveform generator. That means that you have a time-dependent amplitude and a time-dependent phase. In the most simple case, of course, the amplitude is just at 100% and the phase is just constant. That would be a square pulse, like for instance shown here. You can also do amplitude modulation. That means that you now have a time-dependent amplitude. And of course, you can also do phase modulation, like for instance shown here. And of course, you can also combine this. And this is what you can do with the NMR waveform generator using so-called shape pulses. And this then eventually could look like this with a specific amplitude profile and a certain shape phase profile. Now, going back to sort of the basic principle, the first idea of how to do NMR spectroscopy was to just use a constant wave pulse, like an infinitely long pulse, as shown here on the top. If you do a Fourier transform of this, I guess hopefully everyone knows, then you pick up the exact frequency, the carrier frequency of the pulse that you're using. So you get a very narrow frequency distribution here if it's infinite. It's just a delta pulse, a delta function in principle. So this was the original idea, so keeping the constant wave and then sweeping the magnetic field. So what you can do, of course, is that you can then time limit the pulse, and then you are now in the pulse idea. We have a time limited pulse of a certain length, which in this case, of course, looks like a square. And if you do a Fourier transform of this, hopefully also everyone knows that, then you get this sync profile. That means that now, instead of having one frequency in the pulse that you are applying, the RF pulse you are applying, you have a distribution of pulses, or frequencies, sorry. That means that you can excite within a certain frequency window. And that's the whole idea of pulse NMR, how you can do this. And you can, of course, also make the pulse shorter, and then the frequency distribution gets even wider. If you look at this in signal terms, signal analysis term, the way this is distributed is called smearing. And the way that you have some leakage here, this is called spectral leakage. If you look at this in this Fourier transform fashion here. And of course, the way it works, of course, is that you have do a Fourier transform of a box. It's the folding of the box Fourier transform. So it's a multiplication theory of two functions, and then it's just a folding in the Fourier space. So if you do this spectral analysis of the pulse, here's a rectangular pulse here, just normalized to pulses to a length of 1. If you do the Fourier transform of this, as we just seen here, you have the characteristic sync function here. You can then do the absolute values of this and put it in a power spectrum, and this looks like this then. This is very common in spectral analysis, a way of looking at functions, where you have here the frequency here on the axis here, and the power of the pulse here in dBs. And if you look at this, the bandwidth is defined as -3 dB, and this is then the bandwidth of such a rectangular pulse here is 0.9 divided by the length of the pulse. That gives you the frequency range that is within this frequency area here. What turns also out is that if you analyze this, that only 90% of the power frequencies are in this main lobe here. The rest are simply smeared here to the outside of this region. That means that if you use a rectangular pulse, some frequencies are also present out here. This is sometimes what you see as reflection at the spectrometers, because the tune is of course tuned to a certain frequency. For this rectangular pulse, there's a sort of a side lobe suppression, and this is just the maximum here. This is at minus 13 dB, and you have a specific side lobe roll-off. This is for the rectangular pulse 6 dB per octave. And if you do the logarithm scale here of the inverse time here, the pulse, the power mode looks like this. So you want to have this wide as possible, and the roll-off should be as good as possible. So this is the criteria that we want to have for an optimal pulse shape of short duration, is that it should have a main lobe here at minus 3 dB, which is as broad and flat as possible. So the excitation profile is broad, of course, but also fairly flat, so you don't get intensity distributions due to the shape of this. You want to have a high side lobe suppression and roll-off. That means that the energy of the pulse is then mainly centered in the main lobe. And from this kind of analysis, you can see that what you actually want to achieve is that you want to avoid discontinuities in a pulse, and a rectangular pulse where you go from 0 to 100% actually is a discontinuity. And this way you can maybe think about other ways of how to do this. And this is where these WURST pulses, wideband uniform rates, smooth truncation pulses, introduced here in the 90s here by Kupse and Freeman. And if you look just at the amplitude form here, this is just maximum amplitude multiplied by this 1 minus cosine to the power of n. And if you just look at the amplitude on this, we have the shape parameter n here, you have the time and the length of the pulse. You can also set the bandwidth of the pulse. This is of course not relevant here because we only look at the amplitude. So the shape parameter is what we want to look at. So again, here you can just do the same analysis from spectral analysis. Just look at what happens when n goes to infinity. Of course, you get into the limit where you have just a square function. And then your power spectrum looks what you have here on your right. Now, if you then start to decrease n, and also you take here into account that your probe absorption profile has a certain shape, it has a certain Q factor. It could be something like this, for instance, a high Q probe where you have main absorption at your resonance frequency. Of course, this also for sensitivity. And then if you start to decrease the value of n, you see here that the power spectra start to change. And in particular, keep an eye on the main lobe here and also how the roll-off changes. And you can see that it gets broader the lower you get with the shape factor of the amplitude profile. And the wider the main lobe gets. And if you go all the way down to 2, you have basically the same profile here as this, let's say, fictitious probe absorption profile. So with the changing the amplitude profile, going away from a rectangular pulse to this more smooth amplitude modulation, or you can control the steepness of the pulse, of how fast it rises to 100%, and how fast it, of course, goes down, because it's symmetric. And this is, of course, what we want to have a look at. And now we want to look at two specific some cases here. You have with n is an integer or an odd, an even number or an integer number. One can show that the intensity of the one with n equals to 2 is an 0.5. That means that you'll see what that means in a minute. And if you have n equals to 5, there's an intensity difference in 0.6. So you have some reduction factors, which you have to take into account if you want to use this profile. So if you have here a notation experiment, here we've set the rectangular pulse to an F frequency or F field strength of 100 kilohertz. This is the classic notation curve you get here, where you get the 90 degree by 2.5 microseconds and then 2 pi pulse around 10 microseconds. And if you then do the N2 with the same power, you see that the pulse length is suddenly doubled. So you need to make the factor of 2 here, the inverse of this, and then you get the exact same notation properties. So the cost is, of course, you need to have more power, but of course these scaling factors you can then play around with, either do the factor of 2 or 1.5 for the n times 5 pulse. So what you can do, of course, is that you can then either do the same length, then the absorption, the power spectra looks like this. You can also then look at if you have the same length, but then adjusting the amplitude, so you go up to this factor of 2 here, then you get much broader excitation for the same length, of course, at the expense of using much more power. Or you can just also do some length adjusting, so you just do the same power, but make them twice as long. And then you can also choose a compromise, and you can, in this case, you can then match the absorption or power spectrum of your rectangular pulse. So the profile, the amplitude profile of a pulse, you can actually play with this. And one advantage of using this kind of profile has to do with reflected power of such pulses. So here shown now directly from the oscilloscope, where we're taking this data. For the rectangular pulse at a power level 100 kilohertz, for an amplitude shaped pulse here, the WASP shape or WURST shape with n equals to 2 at 100, and then also with n equals to 2 at 200 kilohertz. And you can see here the profile characteristics you have always for the rectangular in red here, and the two different WASP pulses here with n2 at different power levels in blue and gray. And you can clearly see this characteristic. If you put the amplitude to 100, you have a sort of rise time, but you also have a lowering time here at the end, where you get these unwanted power. And you also see this in the reflected power. And the shorter they are, the more also you get reflected power from the WASP pulses or these shape pulses. But they're continuously seen here for the rectangular pulses. So what you can also do then is you can look at the characteristic of this pulse by placing a pickup coil close to the NMR coil, and then you can construct the amplitude versus time here, where you have here the ideal rectangular pulse in red, and this is what you then get from demodulating the signal here. And you see the characteristic rise time and fall time of your rectangular pulse, simply because it has a discontinuity when it goes from 0 to 100. For these N2 pulses, you have exactly a match between the in phase and in quadrature phase as you expected. So the transient effects are much larger by rectangular pulses, as we also know. And for these WASP pulses, it's basically, you can neglect them. So why did we do this? Well, we wanted to understand these WURST amplitude before we go into the broadband case. And what we've used them for is that you can then put more power at the frequency that you have your carrier frequency. And we've tried to use these in the MQMAS. What we did back in 20, we published this work in JMR. We had a look at if we could just replace simply the first pulse here in the triple quantum set filtered version here of the MQMAS experiment. So what you want to do is you want to, in the matrix level, you want to excite your triple quantum transitions here. So what we want to do is we want to compare a rectangular pulse, very short pulse at the power level given here as the subscript here, the superscript here. We've used just simulations here at 10 kilohertz, and as the case for rubidium. And now if we then change just this amplitude shaped pulse, going away from the square pulse here, to a N5 with the same power level. And then you can see here that it's actually performing somewhat better here in the lower range for the CQ values here for rubidium, which is spin 3½ nuclei. So you can actually see the effects straight away just in simulations that by using a shape pulse with a shape parameter, this WASP pulse with a shape parameter 5, you simply press more of the power into where you actually want it. It shouldn't leak out of the pulse. And you can also do this if you then do the length, optimized pulse here, doubling the length here, also with now N2, but also at 200 kilohertz. You can even get more triple quantum excitation efficiency here at the lower range here. Of course, these do not, as also the classic experiment doesn't work for high CQs. So here's just a proof of principle here. We've taken the usual suspect here, rubidium nitrate, and we did the set filtered version here and compared the rectangular pulse here for triple quantum excitation and for reconversion here at 200 kilohertz here, and also now just replacing the first pulse here with a shape pulse with n equals to 2 for this WASP pulse. And you can simply just see just from the colors here that there's actually a gain here that is calculated here on the right here by using the integrals, and you get something like 20 to 25% efficiency simply just by replacing the first pulse with a WASP pulse. And it's just one line in your pulse sequence. We also tested it for aluminum here. This is a mineral ilmenite. It consists of 5 aluminum species here with a relatively broad range of quadrupolar couplings here from 12.7 to 7.6 megahertz here. And now here just comparing the isotropic projection, so this dimension here, the experimental here, and then the fits to this. You can see in general you get something like 20 to 30% more increase in your triple quantum efficiency here for aluminum. We of course did more examples, and if you're interested in this, you can have a look at this paper here in JMR. We also did 5 quantum, and it turns out to be quite even better as compared to rectangular pulses for triple quantum. So the shape of the pulse matters, which one you use. So this is of course an essential part also now in the ultra-wideline case, where we want to apply the original concept of WURST pulses in static and also magic angle spinning techniques. So here's the sequence here using the WURST pulses. This was an idea developed by Luke and Rob back in 2008. And the idea is the following. You have a sort of an echo sequence where you have an excitation WURST pulse here with an n equals to 80. Then you have a refocusing pulse here, which is 90-degree out of phase, either plus or minus, and it has a certain length. And you have some echo delays here. And if you want to, the characteristic of this, of course, that you have an amplitude profile, as I just showed you. Now we have n equals to 80 here, but we now include also the characteristics of the WURST pulse, namely the linear frequency sweep, which you can obtain by phase modulation as a parabola. So the time derivative of the phase is just a constant times the time, and then you integrate it, and then you of course get the time profile of your phase. Because you do these frequency sweeps of both pulses, means that the refocused echo here for each frequency point of your spectrum, equivalent the crystal lights, means that they will refocus at different time points. That means that the criteria you have to set up, that's where it works best, is that this center of this is in the center of the acquisition window here. And you do this by setting the echo delay here. You can put these T2 to whatever you like, 0 or whatever, just ring down delays for the pulse. But this has to be fulfilled. And then you can repeat it in a CPMG type of fashion, and then you can record broadband pulses using broadband spectra using these ultra-wideline pulses. The typical parameters that was used back then and also for some time is that you can use n equals to 80, the bandwidth now of the pulse, of course, which you have to set. And typical length of the pulse was 50 microseconds. And for us, we sort of realized that it's better to describe these in terms of the rate. We'll see in a minute why. And of course, if you think about just the amplitude profile and the sweep, of course, you would imagine that you can excite something with this type of pulse here around a megahertz wide. The basic idea of using these frequency sweeps, linear sweeps, was also investigated a bit earlier here before Luke and Rob looked at this by Schwartz and Ludwig Friedman. And they gave this optimal condition for excitation. So 0.26 times the square root of the rate. And this is then the rate. And the rate you just get by dividing the bandwidth here with the pulse duration. Depending on, of course, what you want to excite, if you want to excite a quadrupolar nuclei and want to be central transition selective, you have to scale the pulse with I plus L half to be central transition selective. But let's have a look at this case here, this formula here. You can, of course, also simulate this, and we did this. We can do this using Simpson. So now here is plotted the RF strength here in kilohertz against the actual flip angle and the intensity, just a single orientation on resonance. And you can see here that the 90-degree flip angle corresponds to, in this case, also here, is given this prefactor here, which is an 0.26. This is exactly what you will read off up around here. It also shows you the advantage of linear excitation. I could show you the same pictures for other types of pulses where the frequency or the shape or the phase is not swept linearly or quadratically. Then you wouldn't have the possibility to excite very broad, but you would have, of course, the possibility to use 180-degree pulses. So in this case, the prefactor, if you want to have an inversion pulse using this WURST type of pulse, you have to be something beyond a factor of 1 times the square root of the rate. Now, of course, we're interested in excitation and refocusing using the same type of pulse. And for this, we use the term here in rate here. And in the later slides here, I'll show you some ideas how to do very slow rates here in this regime here, where you see that the power requirements are very low. But you can also go to higher rates. That turns out to be important if you want to do this under magic spinning conditions, etc. And the unique part about this excitation properties is it's not linear. It goes as the square root of the rate. And this is really, if you think about a rate of 2000, you can have short pulses and large bandwidth for a price compared to a rectangular pulse in terms of power that is fairly low. So what we looked at in the beginning is that we thought, okay, how can we do this? Looking at, again, the central transition for half-integer spin quadrupolar nuclei. And I gave here this in parentheses here with sufficiently long T2. How can we do this? And how can you put the settings optimally? So what we did here is that we started out just using simple spin dynamics here, simulations here using Simpson. And again, here you can see the different rates for the WURST pulses for a fixed bandwidth of 1 kilohertz. And you can see if you take the 50 microsecond one, the shape here is not really ideal. You can see that the 100% here, or perfect excitation, doesn't extend very well. But as soon as you make the pulse slightly longer, like going from 50 to 100 microseconds, it gets much better. And if you want extreme case where the pulse is extremely long, you can see that you get a really flat excitation profile here for a very low rate of 2 kilohertz per microsecond. Taking the slices here at these optimal conditions, which is this refactor to the RF here, the optimal conditions here for the rate of 2 here as in black here for 10, 20, and 40 for the same bandwidth as shown here to the left. You can see the characteristic that if you do a too fast rate this is again for n equals to 80, you get oscillations of your excitation profiles. This is not what you want. You want to have something that's flat, so you have spectra that you can rely on. And then you want to have more of a slower rate, so something below 10. Same if you then reduce, of course, your bandwidth here going down to 400 kilohertz. You can see if you do a fast rate at 40, the pulse duration is 10 microseconds. You can see the oscillations here are really dramatic. So it's pulse excitation artifacts simply due to the amplitude shape combined with the linear frequency sweep. So be careful when you use them. You have to think about which ones you use. Also, if you deal now with quadrupolar nuclei, half-integer quadrupolar nuclei, they have a central transition, and this is what I've shown here for chlorine. Chlorine is a spin 3/2 nuclei, and this is just a simulation here of CQ 10 megahertz and an asymmetry parameter of 0. And having a CQ of 10 means that you have a clear quadrupolar line shape with this second order broadening on it. It means that the frequency dispersion of the crystal light here under defining this line shape for the central transition follows this black line. Now, problem with this is that you also have underneath here, you have also the satellite transitions. Normally you don't care about these, but they are also there. It means that if you excite here, within this range, you will also have some so-called non-selective excitation of your satellite transitions. That means that you have two of them, one from each side, and you can see here these crystal lights with a specific beta angle here. If you look at how the projection onto the line this characteristic polynomial here, you can see that what you get here is that you have non-selective excitation here in exactly this bandwidth here given with this blue line here for both of these. So you can have some leakage when you're looking at your central transition. And this is then now for a bandwidth of 600 kilohertz for your WURST pulse. This is now shown in a bit larger scale here because now we want to compare what happens now if we double the bandwidth of your WURST pulse to 1200 kilohertz. And in this case, of course, now we have the bandwidth here also reflected here at the bottom. It's 1200 kilohertz, and here is the pulse bandwidth. So now you're also hitting the satellites outside of what you're actually interested in. And this means that now the projections here onto the axis here where you have non-selective excitation gets even worse. So you have here spectral leakage potential. Now what we've done here, we took some model compound, potassium iodide, we looked at this at 300. It has a CQ of 21 megahertz and a symmetry parameter of 0. And this is also just to show that the simulations or the configuration that we did are actually true. So here is the bandwidth now of 400 kilohertz. So it's even a little bit more wide than the actual central transition. And here you can see the problem that if you now change the rate, if it's too fast, you see modulation on the line shape due to pulse modulation artifacts, or these artifacts from the pulse. But as soon as then now you turn down the rate here, put the rate down to 20 or 10, you can clearly see, especially the singularity here, gets even better. But you can also see at this leakage point here that I pointed out on the previous slide is now also still there. So you need to be careful that there is intensity, but it's simply just leakage because you have to the satellite transition. Now again here for 400 kilohertz, let's remember this profile depends on the bandwidth of the rate that you have. And here another comparison here between two different pulses, either WURST pulse with 400 kilohertz bandwidth and 800 kilohertz bandwidth. Again, the 400 more or less fits around this the quadrupolar line shape. But as soon as you go beyond the width of this, you can have even more artifacts due to non-selective excitation occurring to the satellite transition. So basically intensity is lost, and this is what gives rise to this hole here on the right. So if you have something that's extremely broad, what you would like to do is that you, of course, would do a step piecewise excitation of your central transition here and record it in some neural steps. And then be careful when you go to this region. So here are some examples here. This is this compound here with 6-chlorine. We have here 2 different cases here at 2 different magnetic fields, and using slow rates here, slow rates of 2 kilohertz per microseconds and bandwidth of 300 kilohertz or 400 kilohertz, you can do this, and you can see that if you can do it at the 400, you get it in 8 steps, and if you go to the 500, you can do it in 5 steps. And you can see if you just do the projection here, you can see it follows nicely what the actual simulation does. Here's an example of what happens if you then go from 2 to 6 kilohertz per microsecond for the rate. And if you look at the different offsets here, if you have the offset here for the smaller rate here, which is then here, you have the intensity at the discontinuity here. And you can see that again, if you have the 2 fast rates, you have, or the 2 large bandwidth here, you have modulation on the amplitude. Another perhaps even more challenging example here is this platinum compound. Also again, now looking at chlorine, it has a characteristic quadrupolar coupling of 35 megahertz. You can record this, we have a 500 megahertz available. You can do this in 18 steps with this short rate, and you can really see there's almost no intensity. Even this dip, as you would expect here, is not even there. It's partly due to that the eta is unequal to 0. Okay, so rates that are very slow requires, of course, that because the pulses are long, Christian windows are should be a bit longer, that T2 or T2 star is long. So what do you do if T2 is short? And we also had a look at this, also a bit in hindsight. So can we make these pulses shorter? And again, here is the sequence here, and it turns out what we need to do is that we need to fiddle around with the shape parameter of the WURST pulse. And if you do this, you can find some conditions that actually works quite well. Here is a very short, we have termed them ultra-fast WURST pulse. It's 10 microseconds long for different values of the shape parameter. 80, which gives you these amplitudes, these non-uniform of excitation, but then you can sort of compensate this by decreasing your the shape parameter. And you get, say, it's not perfectly flat, but it's almost flat. And it's something you don't see experimentally if this is within 2-3%. So you can make it 10 microseconds. You can also make them as short as 5 microseconds here. Now with a bandwidth here of 1.5 megahertz, over here it was 1 megahertz. Also here you have the advantage that you can put n to 10, and then you get really a flat excitation band here in the middle. And of course you can see the price that you pay, that the perfect excitation is only now, let's say something like 600-800 kilohertz, 600-700 kilohertz compared to the bandwidth. So n decreases your effective bandwidth, but it's possible. Of course, now we have a much higher rate. The rate here is on the right here is 100, and also on the right here it's slightly higher. So here's now a comparison also for this platinum compound here, where we compared the classical way of recording, like WURST 80, the shape parameter is 80, bandwidth is 1 megahertz, and then the power requirements, platinum is 1.5, so you don't need to divide by I plus a half, this is 1. So the RF condition for excitation is for 40 kilohertz. This is what's here in black. And now if you do these ultra-fast pulses, so 10 microseconds, n equals to 10, a bandwidth of 1 megahertz, you get this kind of FID, just looking at the spectrometer before Fourier transform. And as you can see, with the same acquisition time, simply because the pulses are much shorter, you sort of compress your FIDs to shorter times. So you can record more FIDs more effectively in the same time. The other benefit also shown here now, comparing the where we just adjusted the acquisition time to be slightly shorter, is that you can see that the echoes, because you're now sweeping extremely fast through your resonance condition, that the echoes, dispersion of the echoes is much, much more narrow. And you can see that the intensity is more or less in the middle. This is why we could reduce the acquisition time to 130 at a little bit cost of some zinc here on top. And this is, of course, if you have more dispersion of your echoes, you need to make sure that the acquisition window is much broader. So just comparing the intensities here, you can see that just going to the ultra-fast WURST pulse, you gain an intensity of 40%. And if you reduce or adjust your acquisition time, you gain a factor of 2 in intensity simply just by using these pulses. And again, if you compare the power levels, it's more or less a factor of 2. Most, let's say, NMR probes should be able to handle this. And what's also more important is that now actually what is possible is that you can now record static NMR spectra for paramagnetic samples. Here's again a comparison now for the classical WURST 80 pulses, the characteristic length of 50 microseconds for lithium iron phosphate and lithium manganese phosphate, compared now in blue here, excited with these short pulses. Of course, now because we went up here to a bandwidth of 1.5, now we have a rate of 150. The maximum intensity requirement of the RF power for excitation is much higher. But again, here we're looking at phosphorus, so it's a high gamma nuclei, high resonance frequency, and this was possible without probes. And just for comparison here, you get something like 2 to 3 factor of 2 to 3 just in gain by using these short pulses. And also this case is actually something that we did before we got to publish this, and you'll see this in a moment, that we can actually use these pulses also now for recording data for lithiated samples. And these spectra were simply not possible without this. This is something like 1 million scans, and if you use the other version of the shorter pulses, just because of compression of the CPMG echoes and the gain of intensity, what that gives this, you get this kind of spectrum, which at least you can give a reasonable fit to. Now, what we then did, of course, we of course want to do this also under MAS. So we want to extend this idea of having WURST pulses and a CPMG train under MAS. And now you need to take care that the sequence is rotor synchronized, and the timings are given up here, and of course you can find them in this paper. We here define some dimensionless parameter, which we call X, just for easy going. So this is a factor, which is if you put the timing, the rotor, if you put the length of your pulse to the rotor period, simply it's just the bandwidth of the pulse divided by whatever width of your spectra you're observing. And again, of course, since these are linear swept pulses, the optimal condition is, of course, given by this expression. Now, what we did here is, of course, to understand, okay, what happens now if we perform these pulses under MAS? And of course, what happens is that you need to make them very short. You can make them a full rotor period or integer number of rotor periods, but nothing in between, either below a rotor period or not. And this is sort of to illustrate what you can do here. You have a carousel here of crystallites when you spin your sample. And these are just the trajectories here of what the frequency dispersion is of different angles here. And then we can play around with this factor here, X, by fixing now the rotor period divided by the length of your pulse to the rotor period, and then it's just basically the bandwidth divided by the bandwidth of whatever you have of pattern. And if it's 1, you get this kind of excitation, and what you want to have is that you want to have it all blue. That means that you have perfect excitation for all crystallized. And you can achieve this even in this case here if x is 4, and you can also achieve it for in some cases for x equals to 2. What this also shows is that the n, the shape parameter, now for these very short pulses doesn't really matter anymore, because you're sweeping so fast through your resonance condition that you sort of have a quasi-static powder during excitation. And this is sort of what this reflects, that we are very fast, very high rates, then you get almost uniform excitation. And does it work? Yes, it does. Here's the, let's say, model compound consisting of 2 platinum complexes here. This is the static WCPMG spectrum recorded at 2 different offsets here and then co-added. This is the simulation here based on the values from the literature. And then what we've done here is that we've spun the sample at 25 kilohertz. We've used 25 microsecond WURST 2 pulses with a fairly large bandwidth compared to what we require here. That means that x is around 9. So we should be able to excite extremely efficiently. And the power requirements for this kind of pulse here is 120 kilohertz, so a rate of 200. Now, just for comparison here, here's the ideal simulation based on the premise up here. We have 2 different isotropic shifts here, marked by these green and red asterisks here. So these 2 are the isotropic lines. And again here, if you compare now directly here with the WCPMG-MAS spectrum here, also recorded at 2 different offset, you see a very extremely good agreement between the mass spectrum here recorded on the WCPMG condition compared to the simulation. So of course, what you need to do to obtain this is that, let me just go one back, is that you have to record here during your acquisition time a number of rotor echoes. This has to be an even number, and then you need to co-add them afterwards, phase them if needed, and then you get this kind of spectrum here. So it works. Hopefully you can agree with me. So now let me just go to the applications. So this is sort of where we are at right now to the development. We have some broadband CP submitted. I'll happy to share with you next time or at conference live. Let's see. But we've used these pulses in some number of projects. So understanding lithiation of tin phases. And first off, Joop here is the main author of this paper. He synthesized these lithium tin phases here. There's quite a few of them. And then he did NMR, MAS NMR, and also WCPMG NMR. So here's just fast spinning here for this lithium-7 SN3 compound. And you can see there are 3 different tin environments in this compound. And they're just characterized by these red circles here. Could do this also with WCPMG, and you can get more or less textbook example of these CSA or shift anisotropy pattern that happens, that occurs in this case. And what you can see here is that the isotropic shift here, or the shift that you get, depends on the number of tin neighbors. Where you have to go to lower, so the hyperfine interaction between the tins here are now increasing, and that means that you can you get chemical shifts or shifts here around 4,000 ppm. We of course, what we did in this case also DFT calculations here using V2K here. This is the values here on the left axis here, and compared them to the experimental ones, and I would say it's a fairly good agreement. So we can also, in this case, get insights on what the different contributions are to the chemical shift here. And this you can, of course, read in this case. And this is, of course, where we use these ultra-wide fast pulses or WURST pulses to obtain something like this. You can also lithiation of tin-based anodes and lithium-ion batteries. And we have Operando setup here, where we have this coffee pouch cell here, where you can connect as a battery here, put it in the stator here, close it, and connect the cycling of your battery here. And then you can record lithium spectra as a function of time. This is what's shown here in green here. This gives you some information, at least you know from the work, and not only from us, but also from the literature. The lithium-7 gives you some information, of course, on what phases actually occur. And there's an idea here of Grandinetti, where you can do the difference operando processing. That means that you just take the derivative of this. And that means that if the colors here are red, you have a formation of a phase, and blue means that the phase is gone. So based on this, you can see, for instance, here that lithium-tin phase here is being developed at a certain number of time. And also, if you compare to the cell voltage here for the different stages here, 1 to 4, you can see different phases that are occurring. So this gives you some information, of course, but maybe tin actually is the better probe here for this process. And what we've done here is that we've taken for different regions here, so different states of charge here for the battery. We've sort of disassembled the battery here. We've scratched off the material of the anode, and then we've recorded this at 30 kilohertz MAS at our 500 here. And then we can, based on the results that I've just shown you, we can just assign different phases. And as you can see here in the beginning, here in region 2, compared to here up here, we can see that the lithium-2 SN5 phase is forming, lithium-tin phase is forming. And then going to higher voltages, you only see here the one phase here. Then if you go to lower voltages, this suddenly gets much more complicated. We see some traces here of what we would assign to lithium-7 SN3, just based on the shift that we observe here. But going back here to this case here at the very low state of charge, we basically see extremely broad tin NMR spectrum. So what this tells you is that the lithiation of here of this nanoparticles goes through this events here, sequence of events here, that lithiation of tin goes via lithium-2 SN5 in a certain state of charge, go to lithium-tin. We have this characteristic, at least based on the shift, lithium-7 SN3, and then you get some disordered phases here, lithiated tin phases, which we don't really know what are. So one case, this is sort of what triggered here, why we thought this was a good idea to use these concepts to this, was this case here, published by Karen Johnson in 16 here, that based on the lithium spectrum here, you can assign different phases. This is then using now this titanium-tin antimony as an anode in lithium-ion batteries. Here we also combine it with pre-lithiation, and they perform better. They have a higher specific charge, and they have a fairly comparable Coulomb efficiency. And we've recorded here for different stage of charges here for 0.2, 0.3, and 0.4 voltage. We can record lithium spectra comparable to what was also. But of course, we wanted to use these wideband ideas, and when you do this, and compared to the phases that you could have expected in this is simply not what we see. We see this very broad spectra, which I also showed you before, that we could fit to something that is more of a lithiated tin antimonal phase, where it's less tin in that you actually expect. So tin, looking at other nuclei than lithium, is actually sometimes very helpful. Of course, you'd require to use these more complicated NMR sequences. So now I'd like to go to another case where we looked at these intermetallic phases here with rare earth elements. So it's based on this rare earth rhodium-cadmium phase. Just to get you going a little bit, what the structure is, and this is what we also use sort of to assign them. It's a crystal structure shown here. It's can be refined using XRD methods to the space group FD, free inversion symmetry or axis and the mirror plane here. And in the project, we looked at different combinations here. And what I would like to show you is this rhodium-cadmium phase here. And what's special about this is that the rare earth elements here sits at the edges, and they have fairly high, really high symmetry. So we expect for the rare earth elements here to have constraints on them that you don't expect any quadrupolar coupling or any broadening due to that you are on a non-symmetry point in the crystal structure. From this crystal structure, we also know that there are 3 different cadmium positions, one here in the middle here, with the mirror plane, one here in the middle, also number 2 here, with a 2-fold rotation axis, and then some mirror planes here perpendicular to this, so the 2 axes is along this one. And then you have also for cadmium here, you have a very high symmetry point here for the number 3 here. This is characterized by this 3 inversion axis and a mirror plane. So you have different environments for the different nuclei. This sometimes is very good to focus on when you want to know what you expect from NMR. And of course, if you look at the formula here, you have lanthanum, yttrium, or ytterbium in here. In principle, you should be able to do NMR on all of them, right? They are all NMR active. Again, some of them are probably more challenging than others, but it should in principle be possible. And yes, it is. So what we did first, of course, we did cadmium here. And now in this part here, I've mentioned all these experimental parameters here up in the right. I'll not go too much into the detail about them. So here we did the WCPMG-MAS NMR at 12.5 kilohertz here for the yttrium phase and the ytterbium phase here, both at 12.5 kilohertz. And as you can see here, of course, I've already marked them. We have one signal here that seems to be depending on the rare earth element, the shift of this. It doesn't show any anisotropy. So this is it is the position in the crystal structure related to the 16C position or Wyckoff position. And for the other cases here, you can see that you get nice splittings here, so you can fit these sideband patterns here, the CSA sideband patterns, easily using whatever favorite program you have for this, Snake or Simpson, whatever. And for this case here, for the signal here to the left here in greenish, we have a more higher asymmetry parameter. So we tentatively assign this to the 96G position. And also here, we have a more lower value here for the symmetry parameter for this CSA or shift anisotropy. So we assign this to the 448F position. Of course, we would need to do DFT to really confirm this if this is the case. But this is unfortunately not so easy for phases that contain intermetallic elements. There are lots of effects that need to be taken into account. And you can do the same here for the ytterbium phase. For the lanthanum phase here, just to give you an example of why it's good to do different spinning frequencies here, is that we have 3 signals in 2 overlapping signals here, which signal belongs to which. You can just follow the isotropic signal, they don't change with the spinning frequency, and then you can see, aha, these are the ones that belong to the isotropic shift. And also for the lanthanum one, you see a slight deviation here for the 16C position. Rhodium is also possible. Again, here we did this at the 500, very, very low rates and very low power. Rhodium is 15.8 megahertz at our 500, and even recording a spectra was actually quite surprising that we could do this. Sometimes, as you can see also on the scale here, you need to look for the signal in these types of elements or materials. This is now at minus 8,000, 9,000 ppm. So if you start at 0, you don't see anything. Of course, the broadbandedness of the pulses helps. And then if you find your signal, you go put your offset onto the signal, and then you can record. And these, of course, are co-added spectra. And we here have a negative knife shift, which we don't really know for sure what the origin of this is, but nonetheless, we can measure this. For the rare earth, we can, of course, record yttrium and ytterbium both of them, at least if you take the 170, 71 isotope for ytterbium, they both have spin 1/2. And we see, as expected, since they're on these cubic symmetry positions, we just see a single line. And again, here it's just also sometimes a matter of finding the signal. For lanthanum, which is a quadrupolar nuclei, it's a bit different. We see we recorded on MAS conditions, so fast MAS conditions. And of course, we expected this also to be just one single line. It's not. So what happens is, of course, is that just everyone who sets the magic angle at KBR should also be one line. It's not. It's simply because you have disorder, you have defects in the crystal structure. This is what gives rise to a certain quadrupolar coupling that we can observe experimentally. We also quantify this by simulating this is an overlap, a pattern overlapping between an isotropic signal and a quadrupolar pattern here. This is something that we also did for antimony some years ago. So, and of course, this is because the quadrupolar interaction is much more sensitive because of the quadrupolar moment of the nucleus to the environment. So it's sensitive to local defects. Last example I would like to share with you is this fast lithium ion conductor. These oxychlorides here based on lithium niobium oxychlorides here. And the idea here was to remove or add more chlorine to the sample to sort of see what happens in this structure. Just to give you a hint on the structure here, this is for the parent compound where X is 0, so lithium niobium oxychloride. There's also from our collaborators here, you can see it's not easy. It's a material that is slightly disordered. You don't get really many reflections. So in your XRD, so it's been a bit of a debate whether the space group was this tetragonal one or this monoclinic one or this orthorhombic one. But you can see at least here, just following the assignment scheme here, that green is lithium. These are located here in between in the unit cell. Niobium is here in the octahedral environments. The two different positions here. Chlorine is at the edges here of your tetrahedra. And if you remove symmetry constraints here, so you have this four-fold axis, of course, going through here, these octahedra, you lower the symmetry, for instance, going to this CC space group. Now the tetrahedra can be distorted. All niobium positions are filled here. And you get this type of structure. So it's a little bit of a debate whether it's one or the other. Maybe it's a mixture. As you see from NMR, this is something we can have a little bit of a look at. We can look at the local structures using some of the probe nuclei. So first off, what they've seen from XRD, if you reduce the lithium content here by this, from going from 1, which is the parent compound, or increase it or decreasing, you can see that the ratio between these 110 and 101 peak decreases. And what this means on a unit cell level here, the different scattering planes also shown, is that if you add more chlorine, you remove oxygen and lithium. So you create interstitial places or defects for lithium to better move through the structure. And then what they say basically is that the interchain distances here decreases in this direction here. So the direction along C here increases. Okay, so what can we do with NMR? Well, again, if you look at the compound, you can do lithium, you can do niobium, oxygen, not so easy. You would need to convince your collaborators to isotopically enrich, but we can try chlorine. The samples I will focus on now are these two 0.9 here and 0.8 lithium content. So here are the lithium-6 spectra here, and for two different phases here, you see two different environments for lithium. You can also detect some lithium chloride from the synthesis, and you can also detect a phase here which actually can do cross-polarization. So there's apparently also a hydrogenated or an OH phase type of phase in the 0.9 phase here. Of course, you can do lithium-7 also, but the best resolution you get from lithium-6, and you can get doing relaxation NMR, just looking at T1. You can, here, represent an example here, you can fit this with a BPP model and get activation energies for all of the compounds here around the very fast lithium ion movement of about 0.15 electron volts. You can do chlorine, and here we did 3 steps, so 3 different offsets here using these conditions here. And as you can see, it's very noisy, and this is actually quite a lot of scans. Okay, it's short D1, but we took this lower spectrum here. You can see the singularities here, and you can fit it. And in this case, we can also see the lithium chloride in here. This is the sharp signal here in green in the middle here. And you can see in yellow here, this is the terminal chlorine, so the 4 chlorine in the octahedra. And if you have now chlorine going into the bridging position as where oxygen was, you would see a signal for this around with a somewhat shorter or smaller quadrupolar coupling. You can also do niobium NMR. And here you can fit the data equivalently to 3 different compounds or 3 different environments for niobium. Give you a little bit a hint on how we did this on the next slide, and then I'm through. That we can assign different niobium environments when we have a hexagon, 6-fold coordinated, a 5-fold coordinated, and a 4-fold coordinated. So basically the oxygenated species are still in there, but you also see some chlorine going into one of the oxygen positions in the structure at this position. So how can you then make sure that, again, that this line shape actually, you could just fit it, of course, and say, okay, that looks fine. But here, how do you make sure that this is actually the underlying line shape of these 2 signals actually are the signals that you're seeing here? Niobium, you can't do MQMAS simply because in this case, the quadrupolar coupling constants are too high. So what you want to do, Rob and some of his students made some idea of how to do inverse Laplace transformation. We made a poor man's version of this, but it has some requirements. It requires that they have a complex line shape, of course. And the trick is that if you have overlapping NMR line shapes, you can simply separate them if they have different T2s. And this you record basically using your CPMG echo train or WCPMG echo train. And then the intensity during this decay of your signal will be modulated by T2. If they're the same, okay, then you can't do this trick. But if they are different, you can use this trick. And how you do it is in the following way, is that you find a spectral point normalized to this point, and then you Fourier transform, co-add the echoes to the first echo, and then you normalize it to this point. And also here, you notice that this breadth here is 1 megahertz. And then you see, if you normalize to this, you sort of remove the T2 effect from this position, and you see differences in T2 at other places in the spectrum. That means that if you combine this and subtract from your full spectrum the difference from the difference here, you can actually create the high T2 side here. This is sort of the fit that we can do to this. And in the other case, you can also then normalize to the other case extremity here, and then see differences in T2 on the other side here. Of course, if T2 is the same, you won't be able to use this. And also you need a spectral point in your spectrum where signals are not overlapping fully. And also here you can subtract them, and then you can get the T2 side with the lower T2. And then you can combine them just using this optimized fit and use this as input for your actual spectrum. So this is a way that you can actually use the echo train that you have anyway from the WCPMG technique if you have overlapping line shapes to deduce what's actually the underlying line shape, provided of course that they have different in T2.
So what we see, of course, here is two overlapping niobium sites, non-zero asymmetry. And in this case, we can rule out the tetragonal group, at least from niobium. On the other hand, from chlorine, we see that some of the cases for the bridging chlorine, we get an eta of 0. So locally, it's a mixture of both, probably. This is probably why you can't decide the space group from XRD perfectly. With this, I would like to finish. There's been a lot of students involved, PhD students involved, Florian, Jendrik, Jonas, Robert, Max, Job, and Stefan from my group. And we've been collaborating here with the inorganic chemists here in our same building, same university, a group of Rainer Pöttgen and also a group of Wolfgang Sayan. We've also benefited from working with Buka, who were actually brave enough to try these WASP pulses using a lot of power, and the probe didn't break, so that's great. And of course, sometimes you need to develop things, and we have an excellent mechanical and electronic workshops here in our institute, and also been used in this context. This is the group some time ago, half a year ago. With this, thank you for your attention.
Thank you, Professor Hansen, for the wonderful talk. So the Q&A section is open for the questions. Professor Hansen, I have a question.
Yep.
So could you please elaborate on how to optimize the sweep rate and the shape parameters for different nuclei and different bandwidth requirements?
Yeah, so what we normally do is that we have a set of identified bandwidth and shape parameters. In principle, you can just use a simulation program like Simpson to do this. And then at least you can rule out artifacts coming from the shape itself without just disregarding any, you can just use single crystallite simulations. And of course, we do this for optimized excitation conditions. And then that's sort of what I showed. It gave you these 2D plots in the beginning. And of course, you just focus on the excitation properties or the best optimal conditions. So this is what we do. So we have a few out there, and you've seen a few here, like the 10 microsecond N10 N equals to 10 1 megahertz bandwidth. That works quite well. We have 5 microseconds. And soon as you go to the slow rates, or the smaller rates, N parameter doesn't matter too much. But it's better than to use the higher N, because then you get the better bandwidth properties.
Thank you, Professor Hansen. So we have one more question, which is, what about quadrupolar nuclei and possible issues with them for WCPMG or QCPMG? Which is more suitable for them?
Depends. It all depends on the quadrupolar coupling. If quadrupolar coupling is fairly low, there's absolutely no, you can choose either. You can use QCPMG, that works very well. It gives you easy phasable spectra that are you can easily phase. WCPMG is what you need if you have large Qs. We haven't tried this so far, I think not, quadrupolar nuclei on the MAS. Again, it depends, I think. So the main advantage is simply the bandwidth of your pulses compared to rectangular pulses.
So we have one more question from Alex. So hi, Michael, very enlightening talk. Do you see any issues with coupling DFS with your fast and short WURST pulses for static WCPMG?
Absolutely not. It should work, I would say. I guess a bit of optimization is of course required. DFS, you would probably, I think the question goes towards of saturating the satellite transition to enhance the population difference for the central transition.
this would of course work. I think Rob Schurker has done this also in the past, combined with WCPMG, I think.
I hope that answers the question. And now we have one more question from Srinivas. Which is the ideal system to start with using WCPMG?
Depends on the nucleus, right? Which one you want to look at, but I think I think we started out with platinum, in fact. If you have low fields, as we have 2 to 500 megahertz, the CSA is not too broad at the lower fields, and WCPMG statically works fine. You can also try other more sensitive nuclei, but again, the real advantage only comes when the CSA is much broader than what you could do just using normal CPMG without the WURST approach. So it depends on the system.
Okay, that's great. So I have one more question. So this WASP approach, how generalizable is it, like across different magnetic field strengths?
It is general. It works in all fields. It depends on your probe, I would say. How much power you can give into this, and specifically, I would say it also has a little bit to do with the quality factor, the Q factor of the probe. For this is often they are from the factory or the manufacturer. They are often set to a very high Q. And that means that the bandwidth, if you look at it in the top of Bruker software, the wobble curve is very narrow. And this, of course, sensitivity-wise is very good. For the WASP pulses, should work. This is at least our experience that we have with these.
So if there are any more questions, you can use Q&A box to type those. Meanwhile, I would like to ask in terms of the batteries actually. So has these pulses, they have been applied in the case of in situ battery NMR experiments?
Yeah, we've done it. This is what I showed. In situ, we've also tried or considered doing this, using them in operando.
Okay.
We haven't done this so far because often you want to look at lithium, and for lithium it's not needed. There you can just do single pulse. That's fine. But I guess if you wanted to look at different nuclei, this is probably what you should do. Or at least use any CPMG enhancement technique. Of course, you're not quantitative anymore because it's then T2 weighted at the intensities. But at least sometimes it's also just about observing a signal, right?
Yeah. Thank you. So we'll wait for a few more questions if there are any.
Sure.
So I have like one more question. Can you share your perspectives on like using this ultra-wideline NMR and then extracting the parameters using the DFT studies, if they have been done, like, so can they both be combined, and how can like DFT be really used, like apart from Simpson or?
Yeah, I guess depends all on the system that you have. In some cases, the lithium tin phases that I show, it was possible and to get sort of reliable DFT calculations running. But in some cases, I guess it depends on the system. Again, that depends on the nuclei you want to look at, right? So,
Yeah.
of course, you can think about, so if you can, again, what's difficult is calculating chemical shifts and CSA parameters or shift anisotropy parameters. Sometimes it's not the chemical shift, it's actually some other paramagnetic contribution or hyperfine interaction that's the cause of this. This is difficult. What's much easier, this is also what I've done during my PhD, in fact, and also what's, let's say, being pursued in other groups, is to use quadrupolar nuclei as spy nuclei in a structure, for instance, pharmaceutical structures. And there it works about much better because it's much lighter quadrupolar. There's like chlorine or other elements. It works well, I would say. So again, DFT is not easy, and sometimes you need help from the experts, I would say.